Hello legends, in this video I'm going to be showing you how to test and scale your self-hosted n8n instance. I'm going to be giving you the tools that you need to use and showing you the process that you need to follow in order for you to do this for yourself. So there's two ways that we can scale n8n. We can scale it vertically or we can scale it horizontally. So for this video we're going to be focusing on vertical scaling, and vertical scaling is where you have one instance of n8n and then you're just giving it bigger servers. So that's what this table represents. We're going to be vertically scaling one n8n instance, and we're going to be doing that by running through three tests. So our first test is that I've deployed a self-hosted version of n8n on a small server, which is 1 gig RAM and 1 CPU. We're going to be using n8n's benchmarking tool to understand how many requests per second this instance can handle. And this is n8n's benchmarking tool. It's available on their GitHub. I'm going to show you how to download this to your computer and how to run it for your instance. And that's the same tool that n8n uses for their own cloud version performance and benchmarking results. And the reason that we're using requests per second, because that's what n8n uses as well. So they're using workflow executions per second, which is, it's the same thing, it's the same metric. So we're literally following the exact same protocol that n8n uses. Now, once we run the test for the 1 gig RAM, 1 CPU server, we're going to bump up the server to 2 gigs RAM, 2 CPUs, run the exact same benchmarking test. And then the first assumption here is that if we increase the server size, we should see an increase in how many requests per second the instance can handle. Now, the next test we're going to be running is we're going to be going from main mode to queue mode. So at a high level, when you're first deploying your n8n instance, it deploys in main mode. Main mode is like having a restaurant where you only have one employee. That employee is responsible for greeting customers, taking orders. They're also acting as the chef in the back, so they're actually preparing the meals as well. So you can imagine if you only have one employee running your entire restaurant, you're going to be pretty limited in terms of how many meals or how many requests you can service. So n8n has this thing called queue mode, which essentially opens up the ability for you to hire more people for your restaurant. So now instead of just having one person run the entire show, you might have one person dedicated to front of shop to greet customers, take orders, and then you might hire a chef for the back of shop to be able to prepare the meals. That's what we're doing over here. We're going to be running the second test where we actually keep the exact same server size. So we're now going to be isolating only by increasing the amount of workers. That's the main thing we want to figure out here. And we're going to go from 1 worker to 2 workers and then run the exact same benchmarking tests. So now we actually see on the exact same server size, if we now increase the workers, the assumption here is that we should also increase how many requests per second they can service. So the first test was just increasing the servers and keeping the one employee. The second test was leaving the servers the same, but increasing the employees. And now our third and final test is going to be increasing both the server, so from 2 gig RAM, 2 CPU to 8 gigs RAM, 4 CPUs, and also increasing the amount of workers that we have, so from 2 workers to 4 workers. We run the exact same tests over here, and then the assumption is that if we increase both the server and the amount of workers, we should get a big increase in how many requests we can service. So that's vertical scaling in a nutshell. Now, as you can imagine, the actual ceiling over here of how many executions you can run per second is bound by how big the server is and how many workers you can run on that instance. So if after vertical scaling, you find that you need more throughput, so you need more requests per second, you would then go to horizontal scaling. So yeah, typically vertical scaling is your first step, then horizontal scaling is your second step. So horizontal scaling is all about running multiple instances. So as we saw before, vertical scaling is just one single instance. So we take that concept over here, we have the biggest server and the most workers, and then if we find that our demand actually increases, we're able to spool up another instance and another one dynamically. And as soon as that demand diminishes, we're able to bring it back down to just one single instance. So you're just dynamically going up and down based on your demand. So for this video, we're just focusing on vertical scaling. Horizontal scaling is a little bit harder, but if you do want to see a video on this, just comment below. Okay, so let's start by testing our first instance. Now I've got this deployed on Docker on DigitalOcean. I've got 1 gig memory, 1 AMD CPU. These are the actual technical stats. So I'm using a shared CPU. I'm using the premium AMD over here, and I've actually just deployed it on this specific one. So I've got 1 gig RAM, 1 AMD CPU. So next step is to go to the performance and benchmarking page, and then click over here for benchmarking framework. We're then taken to this GitHub repo, and this is the benchmarking tool that we're going to be using to test our instance. So you want to run this on a Docker image. I recommend going to docker.com and then downloading this for your computer, so Apple or Mac, whatever you're running. So once you download and install Docker, open up the app and then click on this button over here that says terminal. Let's take this first command, Control-C, paste it into the terminal and hit run. And this is going to bring that benchmarking tool into your Docker container. Once that's done downloading, we can now actually run the benchmarking test. So I'm just going to take this and I've just pasted it into a Word doc to explain all the different bits and pieces. So over here where it says your base URL, you just need to replace this with your actual URL for your self-hosted n8n. You then want to enter your email address for your n8n account and then the associated password as well. And then over here we have this VUS. So this is just virtual users. And that marries up to this virtual users testing that we're doing. Okay, so the way that a virtual user works is imagine you have that restaurant scenario like before, and a virtual user is like a customer that comes into your restaurant. Now they have a bunch of requests lined up to be able to actually send across to your n8n workflow. And the process is that they'll take one request, they'll fire it across to your n8n workflow, then your n8n will be able to process that request, and then it returns the response back to the virtual user. This is one cycle, so one request. As soon as that request comes back, the virtual user takes the next available request and then pops it back into here to run through n8n. So it's always got a queue of requests. In our scenario, we're going to be testing 5 virtual users to start with, which means that there's going to be 5 active people sending requests simultaneously into our n8n instance. So that's going to look something like this. We've got only one instance of n8n. We've got this virtual user sending the requests, this one also sending requests, and then basically all these 5 people are sending requests. And it all works in the same way that while one request is pending with one virtual user, as soon as that is finished, they send the very next request in line. So then the idea is as you increase the amount of virtual users or customers coming into your restaurant, we should see that eventually we actually throttle how many requests per second we can receive because again, we just got one person working at the restaurant, poor guy. So yeah, we're going to start throttling the amount of requests we get. So there's going to be some like efficiency trade-off. And that trade-off is going to be that it's just going to take too much time for those requests to be processed. So as we actually run this process, this is going to make more sense to us. I'm going to leave it as default duration of 1 minute. So for a period of 1 minute, we're going to have those 5 virtual users sending requests and kind of just snapping the next one as soon as the old one is returned. And then we have the scenario filter over here. So this benchmarking tool actually has a bunch of pre-configured scenarios that it can test on. So back in the documentation, we actually have the scenarios that we can access. So we have single webhook, set node expression, multiple webhooks. So this is just different types of load for our actual workflow that we can use. The default was single webhook. Single webhook is literally just this, but we're going to be running our workflow using my n8n benchmarks, their cloud version again. So webhook trigger and edit fields node. The closest pre-built workflow that I found to this was the set node expressions, which gives us these 3 nodes. So I think n8n uses the webhook and edit fields node, but we're also just going to use the respond to webhook node. Again, this is the default from the benchmarking tool. So once you filled out the command, it's going to look something like this. So I've got my deployment URL, I've got my email address, I've got the password. Now, a quick note is that my password has special characters. So on the start and the end of my password, I've got a single quotation, which is different to what is on the default GitHub command to run. And that's, again, if you don't have special characters in your password, you can run this safely in the Docker terminal. So that means if we run it over here and you don't have special characters, the command will work. But if you do have special characters in your password, you're going to get an error saying that we don't understand the command. Anyway, that was just a little nuance. Now we're going to start off with 5 VUs. I'm going to run it for a duration of 1 minute. And I've changed my scenario filter to set node expressions. So I'm going to copy this. And just to show you, this is my n8n instance. There's no workflows pre-configured here, and I do not need to configure any workflows. I can just run this command in Docker. So I'm just going to paste it. I'm going to hit enter. And now it's going to run the test by itself. It's going to install that workflow in my n8n instance, and we're going to get the results in about 1 minute's time. So if I refresh my page now, we should see that workflow installed. There we go. Benchmark tag and set node expressions. Awesome. So our test finished. Now at this stage, you can literally just copy and paste this entire thing, go into ChatGPT and ask it to explain the stuff for you. But the most important stuff for me is to look at how many virtual users we ran max, which is 5. So I'm going to put 5 into here. And then over here, I have my max requests per second, which is 20.2. So I'm going to put that into here, 20.2. So I'm going to run this test a couple more times, probably for the 20 and the 40 virtual users, and then note down the results. All right, so here are the results. So we tested 5 virtual users, and we were able to have all 5 active the entire time, sending requests. We were able to achieve 20.2 requests per second. We then ran 20 virtual users. So this means 20 people sending requests in. We were able to actually have 20 active users sending requests in, and we were able to achieve 22.1 requests per second. Finally, when we tested with 40 virtual users, we were actually only able to get 16 active users sending requests into our n8n instance, and we were able to achieve 23 requests per second. Now, just to look at these stats a little bit, so when we had 5 virtual users, our HTTP request duration was 244 milliseconds. So that 244 milliseconds is this entire sequence here. So the time spent waiting to actually be fired off, and then the actual loop to go into n8n and then come back and be completed. That's 244 milliseconds. And then we were able to get 5 virtual users concurrently sending requests through at 20.2 requests per second. Our next test at 20 virtual users, we had 20 virtual users the entire time concurrently sending requests, but we went from 244 millisecond duration time to 894. So that means that this loop now, instead of taking 244 milliseconds, it took close to 900 milliseconds. So it's like 3 times longer when we went from 5 virtual users to 20 virtual users constantly sending requests into our n8n. And then for our final test, where we had 40 virtual users, we only had an active of 16 because that request time, this request duration, went up to 1.7 seconds. So that means it took 1.7 seconds for the entire loop to finish. So that means over here, when we actually pumped up to 40 virtual users, the expectation would probably be that we should be able to get at least the same that we had over here for active users. But since we had 40 people, double the man concurrently trying to send requests to our n8n, we now actually had to put resources to like blocking those requests, so to speak. So that's like the equivalent of picking up the phone and saying, sorry, give me 1 second, I'll get back to you, because you already have a live person directly in front of you trying to place an order. So that's why we didn't keep it at 20, we actually dropped down to 16. Now I'm going to be bumping up our server. I'm going to go to 2 gig RAM and 2 CPU. So before I actually upgrade the server, I want to quickly look at this graph of CPU usage. So we just ran a test of 5 virtual users, 20 virtual users, and then 40 virtual users where we literally capped out the system and we can only have 16 active users. Yet it looks like our CPU usage only capped out at roughly around 20%. So then the question I have is, well, if we have one CPU, we only capped out at 20% of that CPU, doesn't that mean we had another 80% to go? So it's going to be interesting when we actually upgrade to 2 CPUs to see what actually happens. We're not even reaching the limits of this first one. Okay, so now to resize, I first have to turn off my droplet. And let's go over here where it says resize. And we can see that we're on the basic machine type, premium AMD, 1 CPU, 1 GB. So let's keep the same machine type, same CPU type, but just find 2 CPUs, 2 gigs. There we go. Basic, premium, 2 CPUs and 2 gigs. Let's click this. Let's scroll down and resize. All right, so now we have upgraded our server. We're using 2 gigs RAM and 2 CPUs, and now my droplets turned back on. So now I'm going to rerun the exact same tests. I'm going to go for 5, 20, and 40, and then get back to you when the results are ready. So here are the results of the second test. And actually, as you can see, there's not much improvement. So at 5 virtual users, we had 20 requests per second, roughly 250 milliseconds completion time. Here we had 19 and 260. At 20 virtual users, we had 22 requests per second, roughly 900 millisecond completion time. Here we had 20 and 970 seconds, 70 milliseconds. And then finally, at 40 configured users, we had 16 actuals. We had 18 here. At 23 requests, we had 21 requests. And again, everything is negligible difference within about 10 to 15% difference. So the initial assumption we made at the start of the video, where we're like, okay, if we increase the server, if we double the server size, we should see some kind of increase in the amount of requests per second that we can handle here, but we don't. All right, so let's look at these performance graphs of our instance. So we have bandwidth, CPU usage, and disk reads and writes. This first clump over here is when we had that first server, so 1 gig CPU and 1 gig RAM. When we upgraded our server, this is the clump over here, 2 gigs RAM and 2 CPUs. So as you can see, both bandwidth and CPU usage actually went down when we upgraded the server. So these guys are not the blockers for us. And actually, we made the assumption that if we increase the server size, we should see an increase in requests per second. Since we didn't, it's actually very important to note that the CPU was not a blocker for us. So yeah, that was the first assumption we made, and that was incorrect. But when we look at disk reads and writes, this is the only one that actually increased for our second test. So this is a very good one for us to zoom into and try and understand what's actually going on here. So there's actually a bit of nuance to how n8n works under the hood, which is important for our understanding of how to scale n8n. So we initially thought that we had this system where we had a virtual user sending requests to n8n. The n8n workflow just processes the request and sends that request completed back to the virtual user, that being one cycle. Now, one thing we didn't actually mention is that n8n has its own database where it logs all these executions. So at a very high level, this is like going into your workflow, then clicking on executions, and then all these executions over here, this is the information that's stored in the database. Now, there is other information that gets stored in this database, but at a high level, this just means that every time you try and execute a workflow, there is some reading and writing going on with the database. In our case, the actual restrictor was the ability for the system to read and write information to the database. That's one of the reasons why these two clunks are actually pretty high. Now, this is a very good segue for us to actually go into our second test because we're just running our n8n instance in main mode, which means we just have one worker. Now, as we discussed before with the restaurant, that worker was taking orders, also preparing the meals in the back of the kitchen. That worker was also reading and writing information into the logbook or the database. So that worker was actually doing so many things, and clearly they were slammed. Like even though we upgraded let's say this is the kitchen, even though we gave them a bigger kitchen, it actually didn't mean they could work faster or better or anything like that. because the kitchen size was not the limiter. It was how many people were doing the job. So in our second test, we're actually going to be unlocking our instance and going across to queue mode. So we're going to be hiring some extra workers to help out with some of this workload. All right, so now in order for us to actually activate queue mode for our n8n instance, we have to make some changes to our YAML file. So this is my original Docker Compose YAML file. This is just a boilerplate file. There's no special configurations here at all. This is what my file looked like before I changed to queue mode. And now when I changed to queue mode, I made some additional changes. So the first thing I changed was that I introduced the ability for us to use a Postgres database. So by default, when you launch your n8n instance, you're using the SQLite database. The limitation there is that you can only have one read-write operation at a time. So even if we upgraded and we had more workers, they would still have to wait for just one operation at a time. So that will be the actual bottleneck. With Postgres, each worker is able to read and write their own workflow into the database concurrently. So basically using Postgres just unlocks that for us. So a quick note here is that if you actually were using SQLite database before, all your workflows, all the credentials, all that stuff is going to stay saved on that database. So for this specific configuration, I'm now upgrading my database to Postgres. When I do this, there's actually no migration of data from my SQLite database to this Postgres database, which means when I next reboot n8n, it's going to be completely empty and ask me to sign up as a brand new user. So what you would have to do in this scenario is either launch your n8n using Postgres to start with, but if you didn't do that before you actually implement this change, just grab all your workflows, all your credentials, export that from the previous database. Then when you launch your Postgres database, just import all those files into your new account. We've also introduced Redis, which is our queuing system. So looking at n8n's documentation here, Redis basically acts as the queuing system. So it holds all the next workflows that need to be executed in a line. And then we've got a bunch of workers in the backend. As soon as one worker finishes their job, it gets the next job from the queue from Redis. And that's how we're able to manage multiple workers. So that's what we've done over here. We've just defined Redis for our queuing system. And then the final change we've made is we've enabled queuing mode. So I'm going to make this file available on my school community. But if you want to copy it for yourself, you can just take a screenshot now, and then again now. Then that final bit, then you can plug it into ChatGPT. You'll then also upload your old YAML file and then ask it to help you with these changes. And then to roll those changes out, you're just going to go Docker Compose down. We're going to be restarting the instance, and then Docker Compose up. All right, so a quick note on workers. As we know, when we first self-host n8n, the default mode of operation is main mode. That's essentially like having that one employee running your entire restaurant. What's happening under the hood there is that n8n actually runs on Node.js, and Node.js is the engine which allows for the execution of the workflows. Node.js, in and of itself, it actually has a max capacity for how many workflows it can execute. So when you flip across to queue mode, when you're introducing workers, you're actually introducing multiple Node.js environments within your one n8n instance. So each worker now has its own engine to be able to execute actions. So when you are transitioning from main mode one employee to queue mode multiple employees, under the hood, you're actually building out multiple engines that are able to do multiple things. Okay, so at this stage, we've now set up queue mode. We have one main and one worker. So that one main worker is actually the front of shop. They're responsible for the triggers and all the time-based events. You can imagine this is that restaurant employee that just stays front of shop and they're greeting customers and they're taking new orders. And then each worker, which we only have one at this stage, is just a chef in the kitchen. They're not speaking with the customers. They're not taking the orders. All they're doing is they're getting a new ticket. They're creating the meal. And then they're putting that meal on a bench ready for this main instance to serve back. So I'm now going to run these next set of tests using the exact same benchmarking tool, the exact same command that we had before, and I'm going to come back to you when the results are ready. So here are the results of using queue mode with 2 employees. So for our first test where we had 5 configured virtual users, once again, we were able to hit all virtual users and service all their requests. So the interesting thing to note is that at very low volumes, the performance doesn't really change too much. So when we had 1 gig RAM, 1 CPU, then 2 gigs RAM, 2 CPU, and then when we had the same server but just having 2 employees, we were still hitting roughly similar results. 20 requests per second at 250 milliseconds, 19 at 260, 25 at 200. So there is a slight improvement using this specific setup, but for the cost increase, you might not really care about that. You might actually just start for very, very low use cases using this 1 gig RAM, 1 CPU. So this test already is giving us really interesting insights. But the real gain is seen as you start amping up and actually sending more requests. So when we had 20 configured virtual users, again, we were able to hit all 20 active as well. But now our requests per second tripled. So we went from 22, 20 to actually 60.2. So this is a massive improvement. And then our response time was 900 milliseconds, 970 milliseconds, 330 milliseconds. So not only did we triple the amount of requests per second that we can manage, we also divided by 3 the amount of time taken to actually service those requests as well. So this is a clear win for scaling using queue mode. And then over here, the most interesting thing is that when we had 40 configured virtual users, for our first test, we can only service 16. Second test, only service 18. For our third test, we were able to service all 40 of those requests. Now, there wasn't a massive jump between 60 requests per second to 65 requests. So the interesting thing to note is that we were actually still very graceful. Even though we were coming to a capacity for our requests per second, our total time to service that request was still extremely graceful at 600 milliseconds, as opposed to 1.8 seconds, which is triple the amount of time, or this 1.7 seconds, which once again is triple the amount of time. So this is a clear win for scaling with workers and their ability to gracefully scale and handle these capacity limits. And yeah, just a massive jump to go from 20 to 60 requests per second, and then also much faster to go from 900 to 330 milliseconds completion time. So now going across to our graphs, we're able to see a lot more of an interesting story over here. So this is on a 6-hour time window, so it might look a little bit funky, but CPU usage, as you see, we were capping out here at roughly 20%, but now we're able to capture like another 10%, so we're capping out just under 30, which means that the additional worker is actually doing more work and taking advantage of our infrastructure. And then looking at disk reads and writes, because we switched to Postgres and we also gave the ability for these workers to be able to read and write their own events during the workflow execution, we were able to drastically reduce the load of the reads and writes onto our instance. So this and this are really good signs for us. So the final test I want to run now is by upgrading our server to 8 gigs RAM and 4 CPUs, and then also adding an additional 2 employees to have 4 employees total. So to do that, I'm just going to turn off my droplet, and I'm going to go to resize. And we're currently on the basic premium AMD 2 CPUs 2 gig, and we're going to go to basic premium AMD 4 CPUs 8 gig. Let's resize this. Okay, let's turn our droplet back on. So now let's go back into the console. Make sure you CD into the same directory that holds the YAML file. We don't actually have to now edit the YAML file again. We can just run this command, which is going to help us scale the amount of n8n workers that we have. So I've run this command to scale up to 3 workers. And now I'm just going to go ahead and run the exact same test and come back to when it's done. So here's the results of doubling our server and also doubling the amount of people that are working at our restaurant. As expected, at 5 virtual users, there's not much gain. We had 24 requests per second, now we have 26, and the time taken is roughly similar. At 20 virtual users, we actually increased our requests per second again. So we went from 60 to 94, which is roughly 1.5 times. And our response time actually dropped a lot as well. So we went from 330 milliseconds to 209 milliseconds. And the interesting thing to note is that at 40 virtual users, we actually saw a dip in our requests per second, but it was still very graceful because we managed to do 454 millisecond response time versus the 600 millisecond response time. So based on this number of roughly 90 requests per second, it's actually a little bit hard to find benchmark results for people that are self-hosting their n8n instance. I did find this community thread where this person was happy that they were hitting 90 requests per second on their self-hosted n8n version. So they actually scaled up and they had multiple workers and they were happy with this result. So I'm just going to assume that this is also a very good result for us. And now I want to spend a couple of minutes talking about some other nuances that I haven't covered in this video, but might actually help you get a higher requests per second in this scenario. So the first thing is that right now we see that we're still not hitting the capacity or anywhere near the capacity of our CPU, which means that if we wanted to, we can actually increase our workers and then give that a test and see if that actually gives us more requests per second, or we could actually decrease the workers because maybe we have too many people waiting for the next item to take from the queue, and there's just a lot of turbulence going on, and that kind of stuff might be mushing with the queuing mode. So the next thing we might want to look at is also the roles of these workers. So right now we're just assuming that we have 3 chefs in a kitchen, but really a successful kitchen might also have a kitchen hand who's responsible for cleaning the plates. By cleaning the plates, maybe we're able to service more customers because we can actually just circulate them a lot faster. So n8n actually gives you the ability to define the roles of some of these workers, where maybe one of these workers is responsible for cleaning the plates or just managing all webhook events. And then these 2 other workers are actually executing the workflows or just being the chefs in the kitchen. So for your instance, you might want to play around with what each worker does. n8n also gives you the ability to set concurrency limits for workers. So in your YAML file for your deployment, you might also run some tests and you might realize that if we have an unlimited concurrency for our workers, maybe that actually throttles us too much because we're doing too many read-write events to our database. So if we just throttle people down to maybe a maximum of 20 concurrent workflows at one time, maybe that'll reduce the workload of the read and write events of the database, and then allow our team overall to actually produce more requests per second. Because we have to remember that there's a lot of moving links in this chain. One of those links is Node.js's ability to actually, like how many workflows can Node.js concurrently run? The next one is, like we just spoke about, what are the roles of each of these workers and where do we need them deployed? Then we also had our database. So we switched from SQLite to actually Postgres to allow all the workers to write their own events. And another interesting thing is that we have this really beefy server and heaps of workers, but we're just testing it with a very simple workflow. So this might not be representative of the actual workflow you need to test against. Your average workflow might look like 5 or 10 nodes. You might have 2 or 3 API calls, 1 LLM processing call, and maybe a couple of code nodes to process some data. If you run this benchmarking test on a 10-node scenario with all those different variables, you will actually get different results to what we get here. So in a way, for this benchmarking test, we may have overdone it with our actual server. The way to think about the difference between the CPU and the RAM is that the CPU is responsible for how many concurrent things can happen at once, whereas the RAM is responsible for how beefy those things are. So CPU is how many recipes we can handle at one time, and then RAM is how many ingredients and how many processes are in each of those recipes. But overall, I think we did a really good job here. We were able to figure out which tools we can use to actually benchmark our tests. We were able to follow the exact same process that n8n uses. We were then able to compare the results between increasing the server, between going from main to queue mode, and then also from increasing the server and increasing the amount of workers. The maximum requests per second that we were able to obtain was 94.2 requests per second, which we saw on a community post for the n8n community. That was actually pretty good for a self-hosted n8n instance. All right, guys, thank you very much for watching. If you've watched to the end of this video, I reckon you're a part of the 10% of people who are looking to upskill themselves technically, in which case I invite you to my school community. My goal with the community is to collect a bunch of technical people so that we can all learn and grow together. I'm looking forward to seeing you there. Otherwise, I'll see you in the next video.